still not done with it and don't know if I'll probably use a late pass. It was just a lot for me.
Anything particular on it?
I mean, yes, but no. I mean, I've sent one over to the post, but you know,
You sent one over to the forum?
discussion. Yeah, just one of them. But there was like, well, which one do I choose? Let's do this one.
Well, let me grab that one. Ah, that's a good one. So from 5-1, okay. So domains are a little weird when you start talking about compositions. So I think that's a pretty reasonable question. So let's look at f of x, 1 over x plus 2, and g of x is equal to, what, 4 over x plus 1. And we want to find the, really, actually, we're just asked to find the domain, but we'll find the function along the way of f composed with g of x. Now, we have to be a little careful when we're doing domains of compositions, because according to our notation here, this x has to be able to go into G. So the first thing we have to do is find any restrictions on G. So go down, look at G. Are there any x's that G isn't allowed to have?
0.
Why 0?
Because otherwise the fraction would be, or no, I guess negative 15. Or is that, what is that?
Oh, that's a,
oh, no, 1. So negative 1.
So negative 1. Okay. So according to G, x cannot be equal to negative 1. So that's a domain restriction, and that domain restriction has to be kept in mind. It's very possible that when we put G into F is going to mess with it enough that that domain restriction gets hidden from us. Does that make sense?
Mm-hmm.
Okay, so then we look at F. So F has a natural domain restriction. What's F's natural domain restriction?
-2.
So X, I have hopefully very conspicuously put it in quotes, X cannot equal -2 in f of X. But X's don't go into F in the composition. What goes into F in the composition?
G.
G, yeah. So G of X is what's going into F. So G of X is what can't be -2. Does that seem reasonable?
Mm-hmm.
So we just find out when is G of X -2. G of X is -2 when 4 is equal to -2 times X plus 1. So 4 is equal to -2 minus 2, -2x minus 2. So what, 6 is -2x. So when x is -3. Fair? Now we also could have done that by finding that composition. That composition would have been a 1 over 4x plus 1 plus 2. And then we could have even simplified this composition by multiplying by x plus 1, multiplying by x plus 1. We would have gotten x plus 1 over 4 plus 2 times x plus 1, which would have been x plus 1 over 4 plus 2x plus 2, or x plus 1 over 6 plus 2x. And then said, hey, 6 plus 2x can't be equal to 0, 0. And said 2x, so 2x can't be equal to negative 6, so x can't be equal to negative 3, and that's our restriction. Notice it's the same steps. It's the same that 2 is being distributed, that 2 was distributed. It's just on different sides of an equal sign down here, where here it's in a denominator. Fair? So either way you want to approach that for finding F's restriction is fine, but we have to consider that G's restriction, notice here it disappeared, right? You know, by the time we look down here at this result, G doesn't, you know, the restriction of -1 isn't causing a problem anymore. But we got here by multiplying top and bottom of this by x plus 1. If x is equal to -1, we multiplied the top and bottom of that fraction by 0. Are we allowed to multiply the top and bottom of that fraction by 0? No. So this operation is only legitimate when x isn't equal to -1. So what's our domain? X where x is not equal to -1 and -3. Tell me how you feel about that.
I mean, a lot better than I did prior to that. I think it's just gonna, I freak out. I was like, oh my God, there's so many fractions. And I put like fractions on top of fractions. And I was like, I don't know what I'm doing, but this is a lot simpler than what I was thinking. So,
Well, and clearing fractions always,
yeah.
you know, makes things better, but also is something that people are resistant to for a while. They want to handle the fractions in a much more, I don't know, cumbersome way usually.
Yeah.
But in general, finding domains for compositions, find the domain for the internal function, and then find the domain of the composition as a whole.
Yeah.
Those two restrictions form the restrictions for the composition.
Well, thank you.
Sure. Anybody else got anything this morning they want to look at? Or did you want to try anything, or try anything else, or look at anything else from the homeworks? I know they weren't long or anything, but am I to assume bliss then? Okay. Well, in that case, we get to look at, sure, send me a thing to remind me. That message will make sense if you, anyway. Did anybody send me an email to have me look at their hand-in homeworks? No? Okay.
Yeah, I did.
Oh,
I will.
okay.
I did right after we talked about it in class that day.
Oh, and I think you also said the one about, or in that same one about looking at the different ways to be able to review stuff, huh?
Correct.
Yeah. I sent our tech person, Annie, a message about that. She should get back to me today, so I should have some ways to adjust that. Okay, I'll play with that. Thank you. So 5.3, we're still not going to be talking really about logarithms in 5.3. In logarithm in 5.3, we're going to be focused on exponential functions, and exponential functions usually goes fairly well. But I do want to make an important distinction, particularly for those of you who are going on to calculus, an important distinction between exponential functions and power functions, because the language is a little bit unfortunate in some ways. So exponential functions are functions whose kind of basic form is y equals b to the x. Now we can put any transformation we want in there. So there could be an a out in front. This could be, +5, or there could be, things being multiplied by that x. So sometimes they might look like, as an example, you might have something that's y equals, 5 times 2 to the negative x plus 1. That's still exponential function. It's just an exponential function that has some transformations on it. Where power functions were functions of the form x to the n, where again we could have being multiplied by a or add things to it or whatnot. The big distinction between exponential functions and power functions, they both contain the phrase exponent and power. We think of exponents and powers as being interchangeable, and they sort of are. Like if I have, like, say, 5 to the third, that's 5 to the third power. That 3 is an exponent. So, exponentials and powers will kind of work interchangeably. But as the title for a function type, when we say what type of function this is, if we have an exponential function, what makes an exponential function exponential is the fact that the variable is in that exponential position. That's where the x is, that's where the input is, that's what's changing. And a power function, the variable is in the base, and the power is a constant. So far in chapter 4, we dealt with primarily polynomials, and polynomials are versions of power functions that have been added together. Rationals were made out of essentially fractions of sums of power functions. And even at the end, we did a little bit of just plain power functions. You guys did that on your own. It seemed to go fine. But where that base was always the variable. The big thing that makes these exponentials different is that the variable is in that exponential position. So that's what's going to make these things behave differently. That's the big deal that we're looking at in this section, is what do we do with what happens with that variable up there. Fair? The reason I particularly mention that, for those of you going on to calculus, you will learn tools that work on power functions that don't work on exponential functions, and tools that work on exponential functions, or for working with exponential functions, that don't work on power functions. And the earlier you can make that distinction between the two, the easier it will be. Because you actually have a rule called the power rule that works on power functions, and you cannot apply it to exponential functions because they're not power functions. So for those of you going on calculus, keep that distinction in mind. We do have some restrictions about this b, though, in exponential functions. To be an exponential function, that b value has to be greater than 0. And to explain why, I want to look at kind of a basic power function. Kind of the most generic power function you will ever look at is good old 2 to the x power. And if we try to look at what the graph of 2 to the x power looks like, 2 to the x power, if we started throwing in values for x, let's say x is equal to 0. 2 to the 0 is equal to 1. 2 to the first is equal to 2. 2 to the second is 4. 2 to the third is 8. 2 to the fourth is 16. That gets really big really fast. That's kind of one of the defining characteristics of exponential functions. They get very big very fast. At 4, it's 16. At 5, it's 32. Then 64, 128, 256, 512, 1020, and 1024. They get very, very big, very, very fast. By the time you get out here to say x is equal to 30, the 2 to the 30th is something like, what is it? I think it's 10 billion. It gets very, very big, very, very fast. On the other side, if we look at negative values, 2 to the negative 1 is 1/2. You guys remember that one, right? 2 to the third is 8. 2 to the second is 4. 2 to the first is 2. So if we continue that pattern, 2 to the 0 has to be 1, because these are all half of the one above. And if we keep going with that pattern, 2 to the negative 1 is 1/2. 2 to the negative 2 would be half that, 1/4. 2 to the negative 3, 1/8, and so on. You guys happy with those values? And if we kept doing that, it would get smaller and smaller and smaller, but it would never even reach 0. So we do have a nice asymptote down there. So it has a one-sided horizontal asymptote. So that's kind of what our classic exponential functions look like. And you'll often hear, particularly in films and whatnot, people will say, the pressure is growing exponentially, to talk about something that's just starting to spike really, really quickly, this kind of crazy exponential growth. Heard a fair amount of it in the modeling for COVID, because bacteria and viral loads grow usually exponentially. So there's all kinds of exponential modeling going on right now.
All right, so I have a question.
Shoot.
Does that mean 0 is pretty much always an asymptote for exponential equations? Or
The base ones, yes.
Gotcha.
Yeah. If we threw a, say, +5 on the end of that, it would lift the whole thing by 5, right?
Yeah.
So the horizontal asymptote would move up to 5. But other than that, yeah.
So there's always going to be at least one asymptote on these.
Yep. And the base
Right.
one's always based at 0. And this does not form a vertical asymptote ever. It just keeps getting bigger and crazy bigger.
But it's always going to have one horizontal one.
Yep. Now, the thing that makes exponential functions exponential, the thing about them is that they grow in this way. And by grow in this way, I mean they grow in this ratio. Every time x moves by 1 unit, the function grows by the same ratio, as opposed to linear functions where they grow at the same value. So if you graph a line, it goes up some amount for every same amount it goes over. So it'll go up its slope. So it might go up 3 over 1, up 3 over 1, up 3 over 1. Where exponential functions, instead of going up the same amount, again, go up the same multiple, the same ratio. So this goes, instead of up by 2, it doubles over 1. and then doubles over 1, doubles over 1. And that's what makes them have this really dramatic growth. Fair? I think I said that a little weird, but so what makes exponential functions exponential is that growth is that ratio growth. And actually these used to be called ratio functions in the Latin long ago. And sometimes you'll hear about ratio growth. And when you're talking about ratio growth is exponential growth. If we had one that was, say, 4/3 to the x, and we graphed it, what that would mean is whatever value we're at, the next value, if we go over 1 in the x, the y's would go up by a multiple of 4/3. You multiply it by 4/3. Go over 1, multiply that result by 4/3. Over 1, multiply that y value by 4/3, and so on, so on. Now, why can't b be negative? Why does b have to be greater than 0? Well, if you imagined b was greater than 0, was less than 0, so imagine we had a -2 instead that was being raised to that x power. For the most part, it would actually be okay. If you take -2 and raise it to almost any power, you're going to get some negative output, like instead of positive output. So at, say, 1, you would get -2. At 0, you'd still get 1. At 3, you'd get what, -8. So it would be fine. And for every number between, well, almost every number between 1 and 3, you're going to get corresponding negative outputs. It would try to behave nicely. But what would happen at exactly x equals 2? What is -2 to the second power? I can see it's making you guys nervous. That's good. It's scary. What is -2 to the second power?
It should be 4, right?
It should be 4. Problem is it's a +4, right? So what that means is there's a hole in that graph and a point up here at at +4 instead of -4. And then it's negative until it gets to 4, and at 4 there's another hole, and that hole is filled at +16. Then it's negative everywhere until it gets to 6, and at 6 it's up there at +32, and there's a hole at y equals -32. And all of that's just weird. It tries to be a perfectly fine function, but it's filled with all these little holes that don't make it an illegal function. It passes the vertical line test. It's a perfectly valid function. It's just a little bit weird, but it's not what we call exponential behavior. So it's not an illegal function. It's just not exponentials. There's actually some interesting applications of those functions, but they're not what we call exponential. So we don't let that b value be negative. Now, I got to put a caveat on that. -2 to the x is actually perfectly fine because this is -1 times 2 to the x. The b is still a +2 there. Fair? It's the parentheses that make it the b, make it bad. This is perfectly okay. It's just all down there. So do be a little careful about that. So that's why b can't be negative. But why can't b equal 0? Because I have it has to be greater than 0 here. Well, let's imagine if b was 0. 0 to the x. Okay, what is 0 to the first power? I'm going to answer for you. It's 0. What's 0 squared? 0. What's 0 to the third power? 0. What's 0 to... What is 0 to the 0 power, by the way? 1. Thank you, Andrew. Which I know is weird. Anything to the 0 power is 1. So it's also a weird looking function. It's a perfectly valid function. It's just weird and not our basic classic exponential. So it doesn't behave like what we think exponential should behave like. We don't call it an exponential function. Anybody upset that 0 to the 0 power like that is 1?
Your calculator doesn't understand it if you put it in there.
No, it doesn't.
Yeah.
Yeah. And actually, 0 to the 0 power is a long discussion. So it's weird. But let's imagine this. If you have 5 and you multiplied it by 0 twice, what is 5 times 0 twice? What's 5 times 0?
0.
Multiply that again by 0?
Still 0.
It's still 0. Okay, I buy that. What is 5 times 0? I could say to the third, but you're just multiplying it by more zeros. So what's 5 times 0 once?
0.
0. Okay. What is 5 times 0 not at all? If you take a 5 and you don't multiply it by 0, what do you get?
5.
5.
Right.
What's the only thing you can multiply by 5 and still get 5?
1.
1. That has to be a 1.
Oh, weird.
That's why anything to the 0 power is 1. That's one of the reasons anyway. But yeah, there's a whole 0 to the 0 power causes all kinds of trouble. Anyway, so that's why it can't be 0, because it causes trouble. That's weird. We do have another restriction here, though, that I haven't listed yet. B can also not be equal to 1. If B is equal to 1, it's not an exponential function. Again, we need a reason why not. Well, the reason why not, imagine we had 1 to the x power. So what is 1 to the first power? 1. What's 1 to the second power? 1. 1 to the third power? 1. 1 to the fourth power? 1. 1 to the 0? Still 1. 1 to the negative was 1. It's 1. It's 1. It's always 1. Again, perfectly valid function. It's technically the line y equals 1, but it's not exponential. It's not behaving in an exponential fashion. It's not doing what exponentials do. It's not perfectly valid function. It's a constant. It's not an exponential function. Fair? So, those are the reasons why we don't let b be negative, 0, or equal to 1. Not because it doesn't make valid functions. It just makes weird functions that don't follow our exponential property. But other than that, b can be anything we want it to be. And it will generate this kind of model. Now, when I say that kind of model, it does kind of depend on what our b is and what gets multiplied or added, what transformations happen to this. For example, if we tried to graph y equals, let's say 2/3 to the x, and tried to look at what that graph would look like, you know, we could start by plugging in points. Let x equals 0. At x equals 0, y is going to equal 1. That point is on every unmodified exponential. When x is 0, you get 1. You got to be adding something to it or multiplying something to it for that to be different. When x equals 1, 2/3 to the 1 is 2/3. And notice right away at 1, we went down instead of up. It's like, but exponentials go up. Well, exponentials change by their ratio. So it did go down. If it was squared, 2/3 to the second power would be 4/9. And you could check 4/9 is a little bit lower. If we go to the third power, that's what, 8/27, and that's definitely lower. Fourth power, 16/81, getting smaller and smaller and smaller every time. Well, what would happen on the other side if we look at -1? Well, 2/3 to the -1 power is 3/2. Well, that got bigger. At -2, we'd have 9/4, which is bigger. At -3, you can see what's happening here, right? It's still an exponential function. It's just trending downward, still asymptotic to Andrew's y equals 0. Just trending downward instead of upward. And this distinction, we do have a name for this distinction. We call exponential functions that trend downward this way a decay function. And we use this to model falling populations,
Life of carbon.
half-life of carbon. Anything with half-life is an exponential decay, but that works for molecular decay, atomic decay, all kinds of things. Where when it's increasing, like the first purple one, we refer to that as an exponential growth. And that models not only, you know, things like bacterial growth and general population growth, but I want to say amalgamation, but you know, things that your body does to put together compounds. They grow in this way. And hopefully we can see what makes that distinction between a growth function and a decay for exponentials is whether this ratio is bigger than 1 or less than 1. If that base is between 0 and 1, then it's a decay. So we can even say if, oops, I don't want to put it that way, sorry. If b is greater than 0, but less than 1, then it's a decay. If b is greater than 1, it's going to be a growth function. That all seem reasonable? So we're not going to do a tremendous amount with exponential functions without looking at their kind of partner logarithmic functions. But there are going to be some things that we are going to look at here. I got to move that 5.3 and 5.4 homework, don't I? You guys are going to need more time on that, right?
Yeah, I was honestly thinking about using the late pass on it. But if you're going to move it, that'd be great.
Most of this, I will. I'll give you a little bit more time on the 5.3 and 5.4. We haven't even talked about 5.4 yet. So most of 5.3 though is looking at graphs and building some exponential models, and it does ask you some end behavior questions like this, say -4 to the 1/4 x minus 1. This is really just a function transformation question. So it's all stuff that you've done, but it is stuff that you're going to have to play a little bit with. So I want you guys to have that time to play with it. Ooh, some of those questions are ugly. Fun. But if we started with this internal part here, the 1/4 to the x, is that a decay or a growth?
Okay.
That's a decay. Yeah. So it's going to go through that point at 0, 1 and have the point 1, 1/4. What's this multiplying by -4 going to do to it?
Well, it's going to change all the points to negative.
Yeah, it's going to change all the y values to not only negative, but also 4 times their size, right?
Yeah.
So it's going to stretch it and flip it upside down. Okay, so it's going to go like that, but be more stretched out. So I guess I could draw it more stretched out. But then what's that -1 going to do?
Everything down by a value of 1.
Everything down by a value of 1. So it's going to move that asymptote from your y equals 0 to a y equals -1. So if it asks about end behavior as x heads towards positive infinity, what's this function heading toward? Well, as we go off towards negative infinity, this function is getting closer and closer and closer to that y equals -1. Fair? As x heads towards negative infinity, what's the function doing? Well, as x heads off in this direction, what's the function outputs doing?
Heading closer to -4.
Well, -4, y equals -4 is right there.
-1/4.
-1/4 is...
Wouldn't it also be
here somewhere.
approaching negative infinity?
Yeah. As we go in this direction, what are the function values doing? They're going more and more and more that way, right?
That was my first thought. And then I overthought it.
And that's different than when we talked about asymptotes before, where the asymptote was the same in both directions. These exponential functions are a one-sided asymptote. So usually one side's going to be a constant and the other side's going to be either positive infinity or negative infinity.
So in a simple form like this, that last number is sort of going to determine the asymptote, correct?
Yes.
So like if this is like -3, then our y, -3 would be our asymptotic value.
Yep, absolutely.
Obviously, that's probably not true in crazier forms, but...
Yeah, but a crazier form, you'd usually be able to simplify it down into this form. So that is actually a fairly good generality. So most of 5.3, you'll be looking at graphs, and frankly, I expect you guys to do 2 things. One, use your calculators a lot, but as you use the calculators, do make sure you're looking at kind of why stuff is happening. Like when you're asked to graph things like y equals, say, 2 to the x plus 4, you know what that plus 4 does to the graph. It takes our basic exponential graph, and it's that plus 4 is happening to the x's, so it's an internal change. So it's taking that graph and moving it that way 4 units, right? You guys remember that from 5 or 3.5. So, as opposed to just graphing it and sketching them out, do think about it in terms of those transformations, but feel free to use the calculator to kind of, verify that what you think is happening is happening. So really, we're just trying to get used to the graphical behavior of exponential functions. And since they don't change very much, it's just exactly how steep they are and what points they go through move a little bit, but their general shape is generally one of those two, either that kind of growth or decay, just moved around a bit. There is a type of question in 5.3, though, that can be a bit tough, and I do want to make sure that we see it or look at it, spend some time talking about it. So given an exponential function, let's say f of x equals ab to the x, so it does have an a transformation on it. And given that exponential, that passes through some points. That passes through, say, 0, 3, and 248. Find A and B. So hopefully what this should seem a little bit like is, given 2 points, you should certainly be able to come up with the equation of a line through those points. You guys remember doing that? We looked at it back in chapter 2, and you also did that like in Math 60 and so forth. So given 2 points, you should be able to make a line. This question is implying that given 2 points, we should also be able to make an exponential function. Fair? So that can be a little tricky. Most of the ones they give you are going to be comparatively nice. They can be worse. And we'll look at one that's a little bit worse here before we go, hopefully. But gosh, we're always happy whenever we see x-intercepts or y-intercepts. So that 0, 3 is going to actually be really helpful. So let's look at what these 2 points tell us. They tell us that we're going to get, well, when our x value is equal to 0, this thing is going to output a 3. This tells us when our x value is 2, we're going to output 48. Okay, so for an input of 0, we're going to get an output of 3. For an input of 2, we're going to get an output of 48. Well, you can hopefully see why it's nice when we're given y-intercepts. What is b to the 0 power?
1.
1. So that's 3 equals a times 1, or a is 3. So when they give us this y-intercept, they're pretty much giving us that a value. Okay, so we can put that in here. So now we know that 48 is equal to 3 times b squared. And then just solve for b. So that 16 is b squared, which means b is equal to plus or minus 4. We automatically disregard the minus because we know our b's aren't allowed to be negative. So our function looks like 3 times 4 to the x. Hey. Sorry. He gets excited.
You don't have to worry about pets. They're everywhere.
So these do tend to be very, very nice when we're given that y-intercept. Unfortunately, when you're not given that y-intercept, they can be pretty not as nice. So before I send you off into the wilds, I do want to look at least one of the ways that can be done. And I pulled up one from the homework, and it's really kind of an impolite one. So I'm not sure if that's good or bad. Is it good to see a bad one?
It's good to see one that's really rough because sometimes the little videos that are embedded cover really simple ones.
Yeah.
And they don't really help with the question that you're trying to answer.
Yeah. So let's embrace the fact that this one's a little ugly. So we still want to build the y equals ax or ab to the x, but our points here are going to be a little bit worse. Not too bad. That 5/16 is just a little bit irritating probably, right? So -2 5/16 and 3 320ths. So what we do know is that there's some ratio between 5/16 and 320 that if we have it grow, 5 times from -2 to 3, that it's going to go from the 5/16 to the 320. But coming up with what that ratio is, it can frankly be a little tough. But there is a nice, fairly nice way to find it. It's just weird. So like I said before, this point means we know that the function will equal 5/16 when the x is equal to -2. So that means this statement has to be true. Also, I'm going to use lots of colors in this one because I want to keep them straight. Also, this function will equal 320 when that x is the third power. And since both of these have to be true, I want to combine them to figure out what A and B are. Now, we could combine them in a couple of different ways. We could combine them either by solving for either A or B, frankly, but usually you solve for A. Solve this for A and then substitute it in to the other one. So like say solve this one for A and then substitute that A into there. Some people do that. But actually what most folks do is they will just take one of these equations and divide it by the other equation. So I'm going to take this equation and divide both sides by 5/16. So I'm going to divide this side by 5/16, and I'm going to divide this other side by 5/16. But I'm going to divide that other side by 5/16 in this form, ab to the -2. I'm supposed to divide both sides by the same thing. But this equation says that 5/16 and ab to the -2 are the same thing. So I'm dividing both sides by the same thing. Is that fair? Why is that helpful? It's helpful because those a's cancel. we're left with b to the 5th. Okay, we got to clean this up. 16 over 5. Whatever 16 times 320 is, I'm just going to leave that as 16 times 320 for now.
1,024.
Over 5. Yeah, I didn't want to know. And that equals b to the 5th. Fair? Still got to solve for b. I'll show you why I didn't want to know what that was multiplied together. That 16 is 2 to the 4th. This 320 is 32 times 10. 32 is 2 to what power? 5th, right. So that's 2 to the 4th times 2 to the 5th times 2 times 5 over 5. Those 5s cancel. And this is 2 to the 10th is equal to b to the 5th. So whatever number that was that you threw out, what 320 divided by 5/16 was probably 1024, because 1024 is 2 to the 10th. But unless you knew 1024 was 2 to the 10th, I'm much happier looking at that 2 to the 10th power. Does that make sense?
Not just take the 5th root of 1,024.
Well, because taking the 5th root of 2 to the 10th is so much easier. That's just 2 squared. Because 10 divided by 5 is 2.
Yeah. You also just do 2 to the 1, or 1,024 to the 1/5 in your calculator and get 4.
Yeah, but I didn't have to do any of that. I'm not saying you can't.
All of this confused me.
Yeah, but hopefully you can see that being able to break these down like this might be handy later. Right?
Well, here's what I don't get. So 2 to the 4th is 16, right? And then 32 times 10 is 320 over 5. So then I guess I sort of get what you did.
Yeah, then made that 32 into 2 to the 5th.
Yeah. See, I wouldn't know all of those off the top of my head like that.
And that's knowing your powers of 2 is handy. But the only reason I really went this direction is because that 16 and that 32, knowing that those are both powers of 2, just made it scream, break it down into 2s.
See, I wouldn't recognize that offhand.
And that's okay.
Multiply everything and divide.
But this is kind of a, hey, start looking for that kind of stuff because it's going to make your life easier. Particularly in this rest of this chapter. So great. We know what B is. I gotta let you go here in a minute. But now we know that 320 is A times 4 to the 3rd. And we could certainly find that A from there, right? So this dividing tool is kind of weird. It's a lot like the elimination method for solving systems of equations. So you've done things like it before when you added, two equations together. Here you're just dividing them instead, but it does take a little bit of getting used to. So play with that. So lots of stuff today to go play with. I will move 5-3 and 5-4. I can move those to, say, Friday. That'll give you enough time, won't it?
Yes.
Okay. I'll do that right this moment, so there's no forgetting. .3 homework to Friday and 5.4 to Friday. And tomorrow we'll talk about financial models in exponents, and then that will force our conversation on logarithms. So tomorrow we'll start logarithms. So go play with that. Bring any questions from that. I know there's a lot of weird manipulation in there, but go play with those and bring good questions tomorrow. Okay? Crystal, you okay with that? As a plan?
I am. Right now I'm checking to see if the turn-in homework, what chapter that was on, because I haven't even looked at that yet.
Oh, what section?
Yeah.
Did include 5.3 and 5.4, which doesn't surprise me. So maybe I should move that too, is what you're saying?
If it's something that we need to know on 5.3 and 5.4 and it's due today, that would be helpful. But if not, we'll figure it out.
Now, I want you guys to jump on working on that, obviously. But I don't want it to be stressful, and I want you guys to have time to play with it. So as long as you guys are like, yeah, we're going to jump on it, but having some time to ask questions and get back to it and so forth, I do want to encourage that.
Appreciated.
Okay, and we do have some flex room in chapter 9 and chapter 10, so it might look like we're starting to get crunched up there, but it's not as bad as it looks. Okay, if anything else comes up, let me know. And I'll talk to you guys tomorrow. Have a good day.
Thank you, you too.
Do the same. Thanks.
Mm-hmm.